From here we continue to name some of the simplest alkanes that we might encounter. So we're going to divide our naming process into a number of steps. The first thing to do is, of course, identify the parent hydrocarbon, which for alkanes is the longest carbon chain. Then we want to number that chain in the direction that gets you to a substituent in as few steps as possible. In other words, when we're counting the numbers, we want that number to be as low as possible. So I have here a couple of compounds that we want to go ahead and number. And to do that, I'm going to switch to my notes. For this first compound, let's try numbering from left to right. So this carbon will be number 1. This carbon will be 2, this will be 3, and this would be 4. And if we go ahead and number from right to left, we would have this carbon number 1, this be number 2, this be number 3, and this is number 4. Now the chlorine atom is the only substituent on this parent hydrocarbon, and we want it to get the lowest possible number. So given the choice, we would prefer 2 over 3. So the numbering is going to be as shown. Let's do the same thing with the next compound. So let me start by numbering from left to right. So I would have 1, 2, 3, 4. So my first substituent I arrive at on carbon number 4. Versus if I number the other way, 1, 2, well, I can immediately make my decision here. We're going to get to the first substituent on carbon number 2. So we're going to want a number in that direction. 3, 4, 5, 6. And disregard this other set of numbers. Now that we have numbered the chain, we want to go ahead and assign our compound a name. We do that by listing the substituents first in the name and precede the substituents by what we call their locant, which is the number of the carbon atom that they are bonded to. Now, unfortunately, the naming process is almost completely backwards. The first thing that we find is the parent hydrocarbon, but yet the parent hydrocarbon is the last part of the name. Before that, we have to list the substituents. So you kind of have to mentally keep some information in the back of your head, namely the parent hydrocarbon, while you're writing the first part of the name. There are also some grammar rules that you should be aware of, namely that when we use numbers, they're generally separated from letters using dashes, and we do not put extra spaces in between letters. So let's go back to our notes and finish naming this compound. Okay, I'm going to move this up a bit, and we're going to assign our name to this compound on the left. So we only have the one substituent. It is the chloro atom on carbon number 2. So we'll write its name as 2-chloro. And then we put in the name of the parent hydrocarbon, which is butane. Notice that we don't put any spaces here, so we just go right into butane. 2-chlorobutane. Now, unfortunately, I didn't give enough space to write down the name of the next compound, so I'll just write the name over the structure. So we have two substituents here. On carbon number 2, we have bromo. And on carbon number 3, we have a methyl. And bromo comes first alphabetically, so we'll list it here. So we have 2-bromo. And now we're going to switch back to a locant, a number. So we need another dash. 3-methyl. And since we don't need any other numbers, we're just going to go straight into the name of the parent, which is hexane. So 2-bromo, 3-methyl, hexane. It will often be the case that we'll see the same substituent in a compound more than once. So if we encounter that, what we want to do is include a prefix which will tell us exactly how many there are of that particular substituent. So we use di for 2, tri for 3, tetra for 4, and from here the patterns become a little bit more obvious. Penta for 5, hexa for 6, hepta for 7 if there were such a number. You're not going to encounter that very often. And we precede those names by the locants, separated by commas. So I think that's easiest to see by looking at some examples. So here we have 2, 3, a dash dichloro. Again, a dash separates numbers from letters. And so this just tells us that there are chlorine atoms on the second and third carbon. Here I have 2, 5, 5, with again a dash, trimethyl. So let's go ahead and take a look at this compound, which has 2 methyl groups, as we'll see, and give it a name. It should be pretty clear by observation that we're going to want to number from the right to the left. So this will be carbon 1, 2, 3, 4, 5, and 6. And we have a bromo on carbon number 2. And we have 2 methyls on carbon number 3. So the name here will be alphabetically, bromine comes first, so 2-bromo. And now both methyl groups are on carbon number 3, so we're going to write 3, 3, dash dimethyl, and the parent is hexane. Two bromo, 3,3-dimethyl hexane. In assigning a name, the prefixes are generally not considered. So, for example, if we have dimethyl, the di is not included when you alphabetize. Instead, it's alphabetized as methyl. So it doesn't matter if you have dimethyl, trimethyl, tetramethyl. We always alphabetize methyl as if it begins with M. The same is true for when we use the prefixes sec in sec-butyl and tert in t-butyl. They both are treated as if they begin with the letter B. Now, when we look at iso, so isopropyl, isobutyl, those are treated as if they begin with the letter I. So if we had to compare isobutyl and isopropyl, of course, isobutyl would become first. They both have ISO, but B comes before P. So let's take that into account in naming this compound. The name of this compound is going to be somewhat longer from everything that preceded it. So let's start by identifying the parent hydrocarbon. If you examine this carefully, I have drawn this from left to right, as you'll see. And we're going to want to number this so that we get to a substituent in as low a number as possible. So numbering from the left would give us 1, 2, 3. The first substituent would be on carbon number 3 right here. And numbering from the right, that would get us to our first substituent on carbon number 2. So it looks like we're going to want to number from the right. So let's go ahead and do that. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So my parent is going to be decane. So let's identify our different substituents. So on carbons 2, 5, and 8, we have methyl. So that begins with an M. On carbon 6, we have an isobutyl. And on carbon number 7, we have an isopropyl. So of those, alphabetically, isobutyl comes first. So we'll list that first in the name. So we have 6-isobutyl. Then on carbon number 7, we have isopropyl. And finally, we have our 3 methyl groups on carbons 2, 5, and 8. So we have 2, 5, 8. And this will be trimethyl, followed by the name of the parent, with no space, decane. Six isobutyl, 7-isopropyl, 2,5,8, trimethyl, decane. Now let's go back and refine our approach to step 2. It will occasionally be true that when you number the parent hydrocarbon, you would get to the first substituent in the same number of steps, going from either side. And if that's the case, then what you do is you continue on to the next substituent. So you'd say to yourself, okay, I'm going to look for the second substituent going from either side and see which one of them gets the lowest number. Of course, you still might end up with a tie there. And so you keep doing this until you can finally break the tie, getting to a substituent in the lowest possible number. So let's take a look at these 2 compounds and apply this step. All right, let's consider the numbering of these compounds. So if I start from the left, I have 1, 2. So I come to my first substituent on carbon number 2. If I number from the right, 1, 2, we see it's the same. So we're going to have to continue on to the next substituent. So from the left, I'd have 4 as the next substituent, but going from the right, I would have 3. So 3 is less than 4. We're going to number from the right. Let me get rid of those numbers here. And we'll have 4, 5, 6, 7. Okay. So we have a couple chloros and we have a couple methyls. Chloro comes first alphabetically. So the name here is going to be 3, 4 dichloro. Then we have 2 methyls. So 2, 6 dimethyl. And the parent hydrocarbon with 7 carbons is heptane. So we have a similar looking compound to the right. So I think you see that if we go from the left, we'd get 1, 2. If you go from the right, it'll be 1, 2, so there's a tie. Continuing on, the next substituent would be on 3. Continuing from the next direction, it would still be on 3. And so if we continue on to the third substituent would be on 4 if we're going from the left. If we're going from the right, it wouldn't be until carbon number 5 that you'll get to another substituent. So 4 is less than 5. We're going to want to number this time from the left. And so the numbering is 1, 2, 3, 4, 5, 6, 7, 8. So the parent is octane. So we have 3 chlorines and 2 methyls. Again, we alphabetize with chlorine coming first. So the chloros are on carbons 3, 4, and 6. You'll notice again those numbers are always listed in order. So we have 3, 4, 6, 3 chlorines, so trichloro. And then the methyls are on carbons number 2 and 7. So 2, 7, dimethyl octane, the parent. Here's a good demonstration of the fact that we are not looking at the prefixes when alphabetizing, because chloro alphabetically comes before methyl, even though di comes before tri alphabetically. Now, it will sometimes happen that you can go through the numbering of all the substituents and still fail to break a tie. So if we can't break a tie by counting substituents, we're going to resort to alphabetizing the different substituents and giving the ones that we run into alphabetically first the highest priority. So let's take a look at these two examples here. We're now on page 4 of the notes. I think it's easy enough to see that if you number from the left, the first substituent you get to is carbon number 2. That would be chloro. Let me go ahead and write that out anyway. And if you go from the other direction, the first substituent would be bromo, also on carbon number 2. So to break the tie, you would continue on 3, 4. So the next substituent would be on 4. And if you continued on the top, the next substituent would also be on 4. And since there's no more substituents, we can't use the number of substituents in order to break the tie. So we resort to alphabetizing the substituents. So bromine alphabetically comes before chlorine, and so I'm going to number so that bromine gets the lower possible number in this instance. So that is the correct numbering. And alphabetically bromine comes first, so the name here will be 2-bromo, 4-chloro, and the parent is pentane. Bromo 4-chloropentane. Let's go ahead and use the same logic with the next compound. You'll see that it's a tie regardless of how you break substituents. So first substituent's on carbon number 2, second one on number 3. Next one on 5, next one on 6. And it's exactly the same if you number the other way. First on 2, second on 3. The next one on 5. And then 6, and then we run out of substituents. So either way we go, the numbers can't be determined simply by the position of the substituents. So going from the left, the first substituent is methyl. Going from the right, the first substituent is also methyl. Okay, so now let's go from the left to the second substituent. So on carbon number 3 here, that would be methyl. On carbon number 3, going from the other side, it would be nitro. Methyl alphabetically comes before nitro, and so that's how we break our tie. So we're going to use the numbering there that's on the top. Okay, so methyl alphabetically comes before nitro. So we're going to list our methyls first. So we have methyls on carbons 2, 3, and 6. So that would be trimethyl. And then we have the single nitro group on carbon number 5. So that would be 5-nitro. And the parent is, with 7 carbons, heptane. 2,3,6-trimethyl 5-nitroheptane. Step 1 is occasionally problematic as well. So we're trying to determine the longest hydrocarbon chain and assign it as the parent. But sometimes you'll find that you can come up with two distinct chains, and you'll have to be forced to choose between one of them as the actual parent hydrocarbon, which you have to number. In this case, you will want to determine the parent hydrocarbon such that it includes the most substituents. Let's take a look at an example where that applies here. This next molecule is perhaps the trickiest one we have seen. A lot of people will take a look at this and they'll notice that the parent hydrocarbon has 7 carbons, and they'll say, oh, that's an isopropyl there, and they'll want to name this 3-isopropyl heptane, which, as we're going to see, is incorrect. So let me go ahead and look at my different chains of 7. So I think it looks pretty clear here that this is a chain of 7. And since it's going from left to right, our natural inclinations are going to be to want to make that the parent. However, if you look carefully, we also have 1, 2, 3, 4, 5, 6, 7, which is a very different path. It's still going to be 7 carbons long. The difference is the first path, and I know it might be hard to see with the 2 colors superimposed like that. The top path has only one substituent, and that would be an isopropyl group. The correct parent hydrocarbon is going to be the pink one. Let me go ahead and clear this all out real quick and redraw the pink. Because it would have 2 substituents. It has a methyl and an ethyl. So we're going to go ahead and number in the direction that gives us the lowest possible number on the first substituent, and that's definitely going to be from the bottom right there. So we have 1, 2, 3, 4, 5, 6, 7. Alphabetically, ethyl on carbon 3 comes before methyl on carbon 2, so the name is going to be 3-ethyl, 2-methyl, and the parent heptane. Three-ethyl, 2-methyl heptane. At this point, you should be able to assign names to a wide variety of alkanes. In the next video, we'll continue by looking at how to name cycloalkanes, as well as how to assign common names to some simple alkyl halides. Thank you.